All right, let's do more trigonometry. And in this video on trigonometry, we're going to be talking about trigonometric functions. Yeah, surprise, the thing we've been doing with all of our material, which is doing functions about it, also applies to trigonometry. Before we dive into it, there's a couple things we can kind of discuss about it. Primarily, we are going to work in both radian and degree for this, but sort of our baseline is kind of radian. So when you're looking at functions, you can kind of assume it's going to be radian most of the time. Critically, when you're working on your calculator with this, the mode in which you are set when you start graphing is the mode it's going to work on the graphs as well. So I would always double check what mode I'm working in before I start a graph, just like I would before I was starting to do any math with the trigonometry. Another thing is that if you go to your calculator and you look at the zoom function, when you click that, sorry, my calculator is validating. I don't know why. 7 is Z trig. Might be different on some older model calculators, but if you want to zoom 7, it will set up a window that shows kind of like a nice basic kind of window for trigonometry, which has, let's look at our window. It's a little bit more than 2 pi off on either side, and it has a y min and max of -4 and 4 respectively. So that's nice. That kind of gives us a really good picture for most trigonometric functions we'll look at. So that's good. By the way, I've left this whole room if you want to write any of this down. I'm not going to because you've seen me try and write on this thing. It's awful. If I want to, when I'm working on my window, look at anything more specific, just like with normal functions, I can change things. But one thing that you should kind of keep in mind is that I have some tools that'll help me a lot with trigonometry if I want to look at a function in radian. One thing you might not know is that for my window settings, for example, my x min, I could put -2 pi, and it will allow that as an input. So -2 pi, maybe +2 pi for my x max. And then maybe I want to look at my scale. So XSCL, that's our x scale. What if I want to do that as like pi over 4? Nice. And then my calculator will put those nice little lines up so that I can actually, do the work that I want to do with that function. And that's really handy. So those are a couple things that can help you out with your graph. Don't forget that you can change those as much as you need to. Yeah, and you've also got second function table, which you might find helpful, although it's values of like natural numbers, or integers, I guess, so not as helpful. When you're doing like second function calculate value, don't forget you can also put in something like pi over 6 there, and that'll give you a nice value for specific parts that we're actually looking for. So yeah, essentially I could boil this down into, remember, pi is a button on your calculator. Hopefully you don't need me to say that. Anyways, let's take a look at a sinusoidal function. So a sinusoidal function is specifically a periodic function that forms a wave based on a trigonometric ratio, the sine function. I'm not going to write that down, I don't think. Now, both sine and cosine functions are sinusoidal. They both produce the same sort of curve. And in fact, the curve that I've posted below is y equals sine x. And so with this, we get this nice looking wave. And so a sinusoidal function will produce this sort of pattern over and over again. Now, it's not always going to look exactly like this, of course, because we can mess around with its values. We can do transformations on it. We can put different information in, but it's always got this general shape. And sort of the qualities of this that we're going to focus on are our period, amplitude, and a couple other little bits and pieces. So for our period, when I say our period, if you take physics, when I brought up period, all my physics kids just said, why don't you just say wavelengths? And that's a good idea. The period of a function is the kind of domain of our x over which it takes our function to produce a full cycle, or again, a wavelength. So in this case, our period would be equal to 2 pi. So this is essentially our wavelength, or the domain over which the function does a full cycle. Okay, our amplitude is talking about how kind of how significant our peaks and troughs are. So if we look at our function here, we can see there's kind of like a midline. So we have the x-axis here, which I'm drawing again, not that we really need to, but that x-axis there is what we call our midline. And so our amplitude is the magnitude that our peaks and troughs are away from, that's not the best math word, but away from our midline. So for example, here, our peak, our maximum in this area of our graph is 1, and our minimum in this area of our graph is -1. And so what we're able to see is that we have an amplitude, an absolute magnitude of 1. So in this case, our amplitude is equal to 1. And I shouldn't necessarily use a value yet. We'll kind of earn that, but for now I'm going to. And another way I can calculate this is that I can take my minimum. Actually, no, we should do this a slightly different way. What can I do? Yeah, I can do this. Okay, so I'll take my maximum minus my minimum and divide it by 2. So for our example here, that's our maximum is 1, subtract -1 over 2. 1 minus -1 is 2. 2 divided by 2 is 1. So there you go. And this is a formula that I think is on your formula sheet. It might be on a 30-2 formula sheet. I don't know. It's kind of intuitive, I think. Just find out what the middle point in this function is and see how tall it is. There you go. That's our amplitude. Okay, other key points. When we look at this, it's kind of important to consider that if this is our function that kind of continues in a wave, it helps us to maybe think about a starting point. And particularly for this starting point, we might want to focus on something like an x or y intercept. So this one's a really nice point. We've got the point 0, 0 in our function. And so with this, we might want to look for intercepts. And if I do a transformation on this function, sort of knowing where you'd expect to have these kind of key points, these intercepts, is really, really helpful. Other key points, obviously, are mins / maxes. That's pretty helpful as well, because, for example, if I know that I'm kind of expecting a maximum at pi over 2, then I can just look and see if it's moved. That will tell me stuff about how my function has been transformed. It also helps, obviously, my mins and maxes to look for my amplitude. That's kind of a no-brainer. So let's kind of talk about how the heck this graph actually comes to be. I'll go ahead and draw a circle here, and then I'll draw an axis through it. Line, I don't know why I chose that color, but whatever. Okay. So if I take a look at a function like, and actually I'll draw another one over here. This is sort of our sinusoidal graph, we'll say. So let's say I take a look at something like the function y equals sine x. All right, so if I'm looking at this function y equals sine x, we're saying that our angle, our input is our x value here, and our output is just whatever the sine ratio is with the given angle input. And so we'll consider this in terms of radian, because radian are better. If I start at an angle of 0, my output is the sine ratio for an angle of 0. And I can think about my sine ratio as essentially just being the y value of my unit circle, and that's it. Like, it's divided by 1. It's divided by our radius, so it's really just equal to our y value. So at 0, we get a y value of 0, okay? Then I'm going to create this new angle. Actually, maybe I'll draw a couple lines here. So let's call that, we'll call that a pi over 6, pi over 4, pi over 3. And then we'll go 2 pi over 3, 3 pi over 4, 5 pi over 6. And that should be enough to start with. Let's do that. So here we go. We got pi over 6 is our starting one. So that's our next x value that we can evaluate. And our height at this point, and actually it might help you to go through and put all the points. This is the point √3/2, 1/2. Now we've got this value 1/2 for our function. And I'm just drawing a sketch, right? I'm not even labeling this. Our next angle is at pi over 4, and we get the point root 2 over 2, root 2 over 2. Okay, so that's a little bit higher. And then finally, we've got root 3 over, or sorry, not root 3, but pi over 3. And this angle produces the points 1/2. And then, yes, there's our root 3 over 2. Okay, so that's a little higher. Finally, we've got this point right up here, which is 0, 1. And so our y value is 1. Okay, then we're going to go down and we're going to go through the same pattern, right? We've got root 3 over 2, root 2 over 2, 1 over 2, and then down to this point, negative 1, negative 1, 0. So we're going to have sort of the mirror of that. So I'll just draw this sort of reflection, and here I go. Now, as we go down, what we see is that we're going to get the sort of same shape, but reflected in our x-axis. And so we get that curve continuing, just like this. Right, I don't need to draw the whole thing, hopefully. And that produces this sort of wave that we expect. And if I go through all these angles, I end up at 2 pi over here as an angle. The next angle that I can go to is coterminal with our angle pi over 6. What would that be? 13 pi over 6, I guess, is our next angle we can really analyze. And that produces the same value. So I end up with a function that will do this. It'll just repeat over and over. It's a wave, sinusoidal. Wow. If I do the same thing with cosine, so let's do cos theta in pink, because dang, is that a good color. Over here, I've got the point 1, 0, so I'm starting here, and then I'm starting to go down, and then we go into the negatives, and then we start coming back up, right? I end up with the same sort of looking function. I've got this nice little wave. It's just critically starting at a different point. And these are not, like, they're not supposed to match peaks and troughs. This is just, I'm sloppy sketching it. But I end up with a function that looks remarkably similar. And in fact, it looks like the exact same function. It's just shifted a little bit this way. And we find that, yeah, that's actually true. A cosine function and a sine function are essentially just translations of each other's. But we're going to use a slightly different phrase for that. Okay, so here's our amplitude. Kind of the big thing that's new for us here is this idea that we can link the idea with the amplitude to a vertical stretch. So yeah, our A value is going to work for that. Consider that if my amplitude is 1, that's sort of my basic form of my sine function, where I have a radius of 1. And if I want to have a higher amplitude, I'm going to have to stretch my function a little bit. So how would I find my function here? Well, I can use this formula if I want, where I take my maximum, which is 5, my minimum, which is -1, and I plug that in. So 5 minus -1 divided by 2, and that's 6 over 2, so that's 3. Or what I can do is just do this thing I call using my eyeballs, and I see that this is my middle line, and then I'll just consider the distance from my middle line to my maximum. And just to double check I haven't screwed up where I drew my middle line, I can see that these two lines from max to middle and from middle to min are exactly the same. Sweet. So there's a cool idea. Let's link the idea of our amplitude with our idea of a vertical stretch, which means we can also link our idea of period with the idea of a horizontal stretch. So our b value in our function, and we'll write the actual form of a transformable sinusoidal function in a minute here, but our idea of our b value that we're used to for a horizontal stretch is going to come into play very similarly. We end up with this value here, which is 2 pi divided by b, and that's for radian, of course, or 360 degrees divided by b. One thing you want to be careful on is that our period is sort of an absolute value, right? So even if our function is kind of reflected in our y-axis or across our y-axis, we're not actually changing the period. We're still getting the same sort of graph. It's just, or like the same sort of quality. It's just we've reflected it. So we want an absolute value for our period. We're not going to get like a negative value. If we do have a negative value for b, that doesn't mean our period is negative. It just indicates that we've had a horizontal reflection of our graph. So here's an example. What is the period of the function of the graph above? Don't get confused. There's no b value given to us. So we can just, again, do that trick where we look at things and see what happens. Here, I like to pick one of the three kind of key points. We can either look at a peak to a peak, right? It's the same sort of position on our graph, trough to a trough, or like a min to a min. Or in this case, I'm really happy that I've got a midline intersection on 0, because that makes it really easy. I'm going to just find my next time I have a midline intersection going the same direction. And that makes it really easy math. I see that my period is pi. Only caveat to that is, of course, I've got another one here, but see how this is going down and this is going up? They're not at the same point in the wave, so that doesn't mean we have a full cycle. Okay, so our period in this one would just be a period of pi. So there's two other things we've done with our, we've done reflections. The one other thing I guess we can talk about is broken into two ideas. A vertical displacement is something that we can use to describe, it's just another way of saying a vertical translation. Okay, and so we're just moving the midline up. So I'm going to just write focus on the midline. Okay, and so yeah, I don't think I'm going to explain it any more than that. It should be pretty self-explanatory. It's a displacement, it's a translation, you're just moving it, and a good place to focus on is that midline. A phase shift is essentially a horizontal translation, and the different phrasing here, I don't really know why we do that, but we do, so just live with it. And when we talk about a phase shift, you are going to get something kind of interesting as far as like a tool goes with this. And that is that you're going to want to kind of base your phase shift on, is it a sine or a cosine function? And if you've got a sine versus a cosine function, you're going to kind of look for different places. So if I'm looking for at a sine function, I'm going to look when is x equal, or not x, sorry, but when is our function at our midline, right? And so when does our y equal, we'll say 0, but again, if we vertically displace, then our midline isn't at 0. Whereas for cosine, when is our y at sort of our maximum, which we'll say 1, but again, if I've amplitude changed and vertically displaced this, my y equals 1 is totally different. And here's the really cool thing. You might be saying, well, wait a second. You're telling me I have two different places I have to look at. How will I know which one's which? Remember, sine functions and cosine functions are just phase shifts of each other. And so if you're given a question that just says, make me a function for this graph, you can choose either one unless it otherwise specifies. If it says, make me a cosine function, then you know you're looking for this. If it says, make me a sine function, then you know you're looking for this one. And otherwise, you get to choose. So for me, I usually default to sine functions because that's just what I've worked with a lot. So our vertical displacement, this one's relatively straightforward. What we can say is it's kind of like that plus k value. Whereas for phase shift, it's like that minus h value. Remember, if I have a vertical displacement that's like going to the left, that's negative. And if we're saying subtract h, or in this case, subtract c, we'll use a different letter just because it's going to end up being kind of like that reversed sign. We'll see that in a second. First, though, let us take a peek at just our general ideas here. So here's the same graph. Let's start with our vertical displacement because that's easier. Our base position for our midline is at 0. So remember, we found that our midline was here at 2. So we can say that our vertical displacement, that's the same function, our vertical displacement is at +2. We'll write that. Okay, and then our phase shift, well, let's consider this as a sine function. I'm going to do that because it says so down here. But let's do it as a sine function, and actually we'll also do it as a cosine function later. So I'm going to look for that kind of 0 point. And again, remember, we cross zeros more than once per period. And so I'm going to look specifically at this point or this point. Yeah, and I can look at either one of these and it's okay. But these are kind of the ones that are going to tell me, okay, where am I looking for this? All right, so I'm going to let's look at this one, and I can say that my phase shift then is negative pi over 2. Now, you'll notice that it's going to be kind of like the mirror of it on this side, which is sort of nice. So I could say, well, it's positive pi over 2. That's not always the case, right? I could end up at like pi over 4 here, negative pi over 4. Then I'd have 3 pi over 4 over here. But sort of remember with our period, it makes sense that it's kind of on either side of that based on our period. If I was looking at cosine, so if I have cosine, my phase shift, now I'm going to look at a peak. I'm going to focus on this one. I could, again, look at this one. It's sort of at that halfway point. I'm sort of cheating. It's not labeled, but I know my period here is pi. And so I can just say, okay, well, I must be negative a quarter pi. So we could say negative pi over 4. Okay, given the original function is f of x equals sine theta, what's a transform form of this function? And I'll start by doing this. When we transform a trigonometric function, we will use the following notation. F of x is equal to a sine of bx minus c plus d. Yes, we changed all the letters. No, they're not different. A and B are the same, but H and K are C and D. I don't know, whatever. It's just what they did. And this is what you'll see on your formula sheet. You can also see the version where it's cosine instead, which is just the same thing, but cosine, not a surprise. So let's go ahead and let's actually figure out kind of what we're doing here. All right. One thing that's important for us is that we've got a couple easy values to put in. So we'll start with the easy values. I'll use blue here for our new formula. Our A value, remember our amplitude was 3. So I can go ahead and put 3, or maybe I'll write down my info first. My amplitude was 3. My C value, we said, was negative pi over 2. And my D value was 2. But for our B value, remember, we can't just put in that our period was pi. We have to calculate our B value. So remember this formula. Our period is equal to 2 pi over B. Okay? And in this case, it's sort of the absolute, but I'm just going to ignore that. Our period was pi is equal to 2 pi over B. So if I want to isolate this, my B value should be, move that up, that down, pi's cancel out, 2. Okay, so that gives me my B value then, which I'm going to awkwardly put down here, of 2 as well. So here's my function. 3 sine 2x plus pi over 2 plus 2. And there's my formula. Now, one thing that you'll notice is that I could actually have written down the other form of this. I could have taken that. It's also pi over 2. So I could have had x minus pi over 2. And that would actually give me the exact same function. So I have a little bit of flexibility here where based on my period, my phase shift has a little bit of wiggle room. Okay, let's look at our next function. We've also got a tangent function we can look at, and it's going to make a disgusting graph. Why? How do I know? What's going on? Well, let's take a peek at it. So remember our unit circle, which I will draw for you because I'm so nice. Here we go. Okay, our tangent ratio, yeah, let's do this. Our tangent ratio is equal to opposite over adjacent, TOA, or in this case, our y over our x. And so we are going to be getting some interesting values here. That was a terrible one. Let's try that again. There you go, Herman. You got this. Leave. Whatever. That's enough. So when we're doing this graph, we're going to get some very interesting characteristics because we know we have zeros for our x and y values at some points. And if I'm doing a quotient, then I'm going to end up with some non-permissible values because Again, you can't divide by 0. Even though we're doing trigonometry, that doesn't change the fundamental rules of mathematics. So let's go ahead and let's look at some of our points here. So remember, our ratio here is essentially equal to our y over our x. Okay, not to be confused with our output of our function, this y value on our circle. So here we've got the point 1, 0. So we got 0 divided by 1. Okay, so that's 0. Over here we have got 1/2 and root 3 over 2. That's a 3. Root 3 over 2. So we've got root 3 over 2 divided by, nope, this is backwards. Sorry, I mixed up those 2 points. Let's try that again. I've got root 3 over 2 and 1/2. There we go. So I got 1/2 divided by root 3 over 2. The 2's cancel out, and I end up with just 1 over root 3, which is small. So we'll put it here. Sure. Next up, I've got root 3, not root 3, sorry, but root 2 over 2, root 2 over 2. So these are equivalent values. So any number divided by itself is 1. Sweet. And then over here, I've got 1/2 and root 3 over 2, this time for real. So the half, the 2 cancels out. So I end up with root 3, which is a little bit more. There you go. Then I've got this point here, and here's our problem. We've got the point 0, 1. So I've got my y value is 1, my x value is 0. That's illegal. You can't do that. So what I form is an asymptote at pi over 2, which I guess is not super surprising if you consider my ratio, but it produces a very funky looking graph, because I end up with a sort of like the classic asymptote swoop over here, like that. And of course it won't touch, but I suck at drawing, so forgive me. Let's go back down the other way. So now I've got over here, this is negative 1/2 root 3 over 2. Okay, oh, hold on. We got a positive divided by a negative. So that's going to output a negative. And that gives us this value here, which is negative root 3, somewhere in there. Then I've got negative 1 because, well, I've already done the math for this. I can just go back and do the negatives now. Negative 1. This point should be over there, but whatever. And then I've got negative 1 over root 3. And then at pi, I have negative, or 0 divided by negative 1, which is just 0. And then I'm going to have down here, oh, a negative divided by a negative. Okay, we're getting a pattern, aren't we? Oops, sorry, that shouldn't be there. Let's do this. Right, we're forming this sort of swoop over and over and over again. Right, and if I kind of started going backwards in my circle, I'd end up with this same oof. And so you end up with a graph that does this. You got nice little swoops over and over and over again. And so it looks really gross when you look at it the first time. I know we were kind of like, what the heck? Like, something's wrong with this graph. Yeah, there are asymptotes, but the asymptotes all make sense. They're very logical if you consider the unit circle. And so that's our tangent function. Now, it's not sinusoidal. It doesn't form that wave, but you should be able to tell that it's got periodicity, right? It repeats itself. It's a pattern. And so the pattern here, if we're looking at it, we should notice that it has repeating points at pi. So a period for our normal tan function is pi. Let's go ahead and let's look at what else we got here. Sorry, before we leave this, you can make transformations on a tan function, but I haven't seen a ton of that. But it follows sort of a similar logic to our basic idea of transformations. We do a ton more with sinusoidal functions. I've seen exactly one question that looked at our reciprocal relationships, and it's just like you don't see it. You don't see it on diplomas pretty much ever. But if you did get that sort of function asked of you, and you had to think of how to do your reciprocal functions, you just draw your unit circle or memorize it, which you should have it memorized, but might help to draw it so that you can follow along as you're going. And that way you can do the same thing we did, create these graphs, but now using those reciprocal functions. Again, not expecting it, really not expecting it, but I guess it's not like 100% off the table. Another thing we can do here is we can solve questions by graphing them. And I will, I don't know if we really need to do practice ones on these. So why don't you go ahead and do these? I'm going to pause the video for 2 seconds and I'll just post my answers. So if you don't want to get spoiled, you should turn off your pause the video. Man, I forgot how computers work. Anyways, turn off your entire computer right now so that you don't spoil it. Okay, so I'm going to put them on in 3, 2, 1. Yeah, I lied. I'm going to go through the second question. But here's your first question. There are your answers. And this one, let me give you a helpful hint. We're going to be looking at putting in our graphing system like this. But take a look at this. So here's a new period for us. When I ask for a general solution, I've always said like plus minus 2 pi n, where n's an element of the integers. That's based on going around our circle. Here, our period is different. So what's our period? Okay, let's calculate that. Our period is equal to 2 pi divided by our b value, which is pi over 4. So our period here is 8. Spicy. Okay, so we have a different period. So when we do general solutions here, I'm going to go ahead and calculate my intersections. There's 1 over here. My graph is low. First curve, second curve, yes. And on this one, we're going to use some rounding. Sorry. I've got my first answer is x equals 0.43. We'll round to 3 plus minus 8n, where n is an element of our, let's say, whole number group, because technically 0 is allowed to. And it's also true that x could be, drum roll, because I should have started saying this after I had already found it. There we go. X can also be equal to 3.567. That's cute. Plus minus 8. Oh, 5, 6, 7, 8. That's straight. N, where n is an element of my whole number family. Cool beans. I'm going to leave the last question for you to do on your own. It is available in your textbook. Your turn, example for page 271. So you go ahead and try that out. And our next video, we'll talk about trigonometric identities, because identity politics are everything these days. That's a bad joke. Okay, bye.